So, hello everyone. Maybe we can wait for 5 minutes before starting the session. I hope I'm audible. Uh, let's just wait for like 5 minutes so that a few others can join the session in person. Till then, I'll just mute myself. Okay, so I guess no one else is joining the session. Maybe we can just get started. So, hello guys, just to reintroduce myself, I'm Lakshya Saggi, the problem solving TA for the NPTEL Social Network Analysis course for the Monday 6 to 8 p.m. sessions. And I believe this will be our fourth session now. And in this session, we'll be mostly talking about like the stuff covered in this week's lectures. It was again a bunch of definitions, so we'll be like trying to revise all of those. Yeah, like trying to summarize all of what was covered in the lectures, and then we'll also try to solve some problems. The main focus this week was more on like link analysis and different kinds of link analysis in networks. So yeah, problems will be related to those only. Obviously, like while solving the problems or while discussing the summaries, also summary of the lecture sessions. Also, I'll be assuming that you guys have at least seen the lecture videos. So uh, we'll be doing a much more higher level overview, like in depth, like you already have the lecture videos present, so you can uh, watch them for in depth stuff, and we'll be mostly discussing more higher level overviews of things because I can't cover in 2 hours like the content covered in 7 lectures. So yeah, so maybe I'll just mute my, maybe I'll just uh, turn off my camera and share my screen. Also, at any point of time, like if there are any issues with my screen sharing or my audio, or like if there are any doubts in between, feel free to ask me via chat, and I'll try to answer it to the best of my capabilities. Okay, so I hope my screen is visible to everyone. If not, please inform chat. So other than that, maybe let's just get started then. Uh, so this is, as I said, week 4, and this in today's session we'll be mostly discussing about link analysis and different kinds of techniques involved in link analysis. So first of all, what is link analysis? Like all of these are mostly just snapshots of lecture slides. I just take them out. Like if you have previously attended my sessions, I just discuss some of the important slides which were discussed in the lecture, so that uh, yeah, we have a high level idea of what are the main things, what are the main takeaways of this week's lecture videos. So what is link analysis? So link analysis is nothing but process of visually representing networks via nodes and links. So on a high level, if you have a large data, like how do you, if you want like visualize data in a more beautiful manner, you can visualize it in terms of graphs, and graphs contain nodes as well as links, which are like just vertices and edges of the graph. And then you can like analyze the graph, and this is what is called link analysis. And what are links? So you can decide to have some node entities in the graph which can correspond to some objects of some real world objects, and then if there are some kinds of relations between those objects, those can be represented via links. So links actually model interaction between various types of entities, and there can be various types of links. Sometimes they are homogeneous, heterogeneous, directed, undirected, weighted, unweighted, signed, unsigned, and so on. And this like uh, so usually while modeling a real world problem in graphs, like only this link analysis part is not important. Another thing is important, which is important, is like what is the representation you are choosing while modeling something. So you can try to model something. Maybe if there is if A and B go together always, then you can have like undirected edge between A and B. But suppose you have a task scheduling problem where task A has one node, task B has another node, and task A always has to be performed before task B. Then you can maybe put instead a directed link from A to B, which implies that A should always be completed before B or something. So note that while we'll mostly be discussing about uh, different ways to analyze graphs, or like techniques to analyze graphs, but note that another important aspect which we are not covering, but it will be it will be specific to every real world problem which you will be encountering, uh, the issue of like how to visualize some problem as graphs. So there can be various models, and then it's really up to the implementer to decide which model is better for modeling a certain problem. So yeah, but yeah, so we'll just be discussing the mathematical nature, like if there's a directed graph, undirected graph, or weighted, unweighted, signed, unsigned, how can you like kind of analyze those graphs? So yeah, so what are signed networks? So signed networks are nothing but so direction of a link in a network captures direction of information flow. Weight captures the strengths of maybe some links, but neither of these things express like whether that thing is positive or negative. Like suppose you have a YouTube video, then a like on it is kind of a positive thing, and a dislike on that is kind of a negative thing. So sign networks are nothing but, so you can just assume that sign networks are networks which have positive as well as negative weights, because if some edges are positive, maybe like we have notion of something being positive or negative. So yeah, so if something is a like, then you can model it as positive. If something is a dislike, then you can model it as negative. For example, suppose node A is some kind of a viewer, a YouTube viewer, and B is a video. Like suppose B is my like lecture video which is uploaded on YouTube, maybe of the previous session. This video is of like D is also my video and C is also my video, but C and D, these two videos, maybe the video C and D which were uploaded by me, are kind of disliked by the student A, but student A liked my uh, video B which I uploaded. So this kind of a network can represent these kinds of likes dislikes relations. So yeah, just an example of uh, what sign networks are, and uh, like how do you perceive sign networks as like in terms of social relationships. So this can be modeled using something called a balance theory, which is kind of POX model. So it's like very specific to maybe real world social like interpersonal relationships. Maybe uh, like this is that. So we are just kind of discussing like what's the use of maybe sign networks. So one use of sign networks is done in like balance theory, which is like which was introduced as a theory of attitude change, and this is also known as POX model in psychology. And what this means is that the essentially what this model states is that an individual tends to choose balanced state in her interpersonal relation. And what this means is if the like you can define some interpersonal relationships to be balanced or imbalanced, and people will likely and any person would like to be more in balanced interpersonal relationships, would not like to be in imbalanced relationships. And that's why like this is more of a model this is more of a psychological model, because it models like interpersonal relationships between humans. And like, for example, suppose you have three people, Pam, Oliver, and skiing. Suppose Oliver dislikes skiing, so there's a negative edge. Pam likes Oliver, and but Pam is crazy about skiing. So these two edges are positive. This edge is negative. Similar, and this kind of a thing, like this is an imbalanced relationship. So maybe we'll come to this later. Like why some. So you look at triads of vertices, like all the triangles which are formed in the graphs, and you can call those interpersonal relationships as balanced or imbalanced. And how do we categorize those? So essentially, what this POX model states is that okay, like how do you classify some interpersonal relationship to be balanced or imbalanced? It's quite easy. Like you will say like balance or imbalance in terms of triads. Consider any three vertices A, B, C, and then if A likes B, B likes C, and C likes A, then A, B, C, all of them can coexist together. They really have no reason to fight. Similarly, if only A and B like each other, but C and A dislike each other, and C and B dislike each other, this is also termed as kind of balance in this kind of theory. And why is this? This is because A and B are so this phenomena, like this is a balance theory because this phenomena can be explained by like A and B being friends because of mutual hate, like mutual enmity to C. So here, like A and B can choose to stay as friends with each other, and both can dislike C at the same time. And no one will want to like walk away from this kind of interpersonal relationship. Like liking or disliking someone is fine. Like you're free to choose, like you can like or dislike, but there won't be any imbalance in this relationship because A and B can coexist together and C can exist separately. Similarly, here A can exist separately and B and C can coexist together and so on. But what are unbalanced triads? So note that there are only like so there are three edges, and uh, all these three edges have two choices: either they can be positive or negative. So there are 2 raised to power 3, which are like 8 kinds of triads are possible. So we see that 4 kinds of triads are balanced, and the other 4 are characterized as imbalanced. And why is this the case? So this kind of a triad is kind of assumed to be imbalanced, where there are 2 pluses and 1 negative, because now A and B cannot coexist together, because if A and B coexist, then A will force B. So B likes C, but A does not like C. So C cannot remain a friend of B. So A will tell either B to maybe break off his or her friendship with C, or maybe B will force A to like C. So right now, like this kind of triad is imbalanced. Similar cases here, like there are 2 pluses and 1 negative. Again, like uh, uh, A and B similarly here cannot coexist together because of here like enmity to C, and like similar case here. And if all of those A, B, and C dislike each other, then again this is a very unbalanced relationship, because then they all will tend to walk away from each other. So like maybe this can be just thought of as a maybe psychological model, which is POX model. And yeah, this example is more to show you like why are sign networks sometimes useful. Then another interpretation of sign networks is uh, this kind of a thing, which is like a status theory, where what status theory states is that like so right now balance theory views sign links as likes and dislikes, and this is why it was used in psychology and stuff. But a sign link in maybe some other model can be interpreted as indicator of like status or prestige of a node with respect to other. So that's why this is called status theory, because these signed edges can assign maybe some status to the nodes. So maybe like if there's an edge from a directed edge from X to Y, which is positive, then this means that maybe Y has more status than X. According to X, so all these edges are originating from X. So maybe you can assume that like X things. So what we can say, how we can interpret this network is maybe X sees all of its outgoing edges. So X sees a positive edge going to Y. So this means that X perceives Y to be of higher status than X. Similarly, there is an directed edge going from X to Z, which is of negative sign. Then you can think of this as X perceiving Z as of lower status than X. So like these statuses can be different. Like this is not an absolute order. Y is greater than X is greater than Z. So this is the status relative to X. Maybe X thinks that Y is like higher in status than X, but maybe Y also has a positive edge to X. So Y, according to Y, maybe X has a higher status than Y. So all of these things can happen, but status theory is more useful for like. So basically, why are we discussing all of this? Why was this all of this discussed in the lectures? Because like so you have a tool which is sign networks, and it is up to you to choose what to do with these sign networks. So one can maybe model like psychological things. This balance theory models psychology in terms of sign networks. Similarly, there's another social phenomena which is like maybe not just social, but also in terms of like mathematical terms. Maybe some nodes want higher status, some nodes have lower status, and all of this can be attributed using these sign networks. So, yeah. So and then different kinds of node metrics. So again, like we can define different kinds of metrics in this status theory. So node level metrics, which can be defined as maybe, so there are some things like generative baseline, which just says fraction of positive signs generated by a node. So maybe like the number of the number of positives. So basically, total signs generated by a node, like the positive signs generated by a node divided by total signs generated by a node, will be the generative baseline, and similarly receptive baseline will be fraction of positive signs received by a node. So number of positive signs received by a node divided by total number of signs received by a node. So generated nodes will be essentially uh, uh, correspond to like outgoing edges, and receptive nodes, like receptive the things received by a node will be just like incoming edges. Outgoing edges are generated edges, and incoming edges are received edges. So for example, for A, how many outgoing edges are there? For A, there is just one outgoing edge, and that is positive. So the total number of outgoing edges is 1, and that is positive. So generative baseline for A is 1. Similarly, for B, there is no outgoing edge, and so there are 2 outgoing edges, but no outgoing positive edge. So the generative baseline for B is 0. Similarly, for C, there is 1 outgoing edge, and that is positive. So again, generative baseline for C is 1. Similarly, receptive baseline can be computed. Similarly, you have to look at incoming edges if you want to look at receptive baseline. Yeah. And then it was discussed like, what do we actually mean by strength of a tie? So like how close are 2 nodes to each other? So this kind of a thing has been discussed previously also, but in terms of sign networks also, this can be thought. So suppose there is a, like, how you want to see like how much is a connection between X and Y, how much strong is the connection between 2 nodes X and Y, let's say. So to capture this sense of closeness among entities or people, one of the methods which is used is like Jacquard score, which we have discussed previously also in previous sessions. So what is Jacquard score? So Jacquard score is just measure something called neighborhood overlap, which is just equal to like the neighbors of, so neighborhood overlap between X and Y is nothing but the number of vertices which are adjacent to both X and Y divided by the vertices which are adjacent to X or Y. So yeah, I think we also did a problem where we tried to solve a Jacquard score for a couple of nodes last week. So yeah, and higher is the neighborhood overlap score, which means that the nodes are closer to each other and have a like higher chance of forming a link in between. So what this essentially, like, all of this is maybe very heuristic level or very high level stuff. So this just says that if 2 people have very similar neighborhood, so to suppose like 2 people like to hang out with similar kind of friends, like have, so 2 people have almost same friend circle, but they do not know each other, then it is very likely that in the future these 2 people X and Y will also meet each other or form a node between each other because they have like same taste in friends. So yeah. So yeah, at least right now we are assuming that things like opposites attract is not true, but what's true is like attracts like. Yeah. Similarly, another, so here we quantified strength using this Jacquard score. Another heuristic which we can use to quantify strength is maybe using triadic closures. And what does triadic closure say? So strength of a triadic closure with respect to nodes A, with respect to node A and the nodes B and C, of which A is a mutual friend, can be quantified using clustering coefficient of node A. So if you guys remember what is clustering coefficient for a node, what's local clustering coefficient, we discussed this I think last week or last to last week. So clustering coefficient for any node is just like, suppose for node A is just equal to the number of edges between neighbors of A. So you take the neighbor, all of the neighbors of A, and note how many edges are present between those neighbors, divided by the total number of possible edges between those neighbors. So something, and the total number of possible edges between neighbors of A would be just like degree of A choose 2, because you can choose any 2 vertices at a time. So higher the clustering coefficient for a node, yeah. Uh, so here, like, we'll be assuming that. So here, like, how do you quantify strength of triadic closure? You quantified strength using these clustering coefficient. So what essentially we are saying is that suppose there is this, there are these nodes A, B, and C, and right now B and C don't have a node between each other, but you want to see how strong is the tie between B and C. Like we quantified strength here using Jacquard score. Similarly, we can quantify strength between B and C here using also like triadic closures. And what this means is that so B and C have a common vertex A. And so how likely is it that this kind of triadic closure will be made in the future? Right now, there is no edge between B and C, so this is not a complete triangle. But with how much probability will it get completed in the future? So this is just like, so B and C will become friends in the future. Uh, the probability for this is just equal to clustering coefficient of A. This is like, again, like we don't have, like, this is not a proof or something, because like this is a claim, and like this is how we are trying to model some relationships, and yeah, this is kind of a heuristic. So we say maybe like if clustering coefficient of A is high, then this means maybe all the vertices in neighborhood of A are kind of similar to each other. And that's why any two vertices which don't have a bond but are neighbors to A will likely have a bond in the future. So if you consider this triad ABC, then the probability with which B and C will form a bond in the future will be just equal to clustering coefficient of A. And clustering coefficient of A is just degree of A choose 2 in the denominator, which is just K times K A minus 1. So K is just degree of A. So K times K minus 1 divide by 2, and divide by 2 becomes times 2 in the numerator. And here you will just be summing over number of edges present between neighbors of A. So for all ij belong to neighborhood of A, if there is an edge between I and j. So nothing too fancy, like quite easy. So this is just the definition for clustering coefficient of A, which we have already done. So yeah. And usually, like rather than Jacquard score, I think this is a much better metric for quantifying strength of triadic closure. There can be much more sophisticated metrics also, but for now we'll just be discussing these. Then we discuss like what is Dunbar number. So Dunbar number is okay. So maybe right now we are not assuming any limits on like degrees of graphs. So like what we are assuming right now is that a person can be associated to maybe any number of people. Like if there are n nodes in the graph, like a node can be like associated or have an edge to maybe n minus, even n minus 1 nodes. But in real world, maybe this kind of a thing also breaks down. So this was this study was done by Robin Dunbar, who kind of showed that maybe like humans don't have like, and this is like quite intuitive also, like humans don't have like infinite social limit, or maybe cognitive limit, that like you cannot maintain very close relationships with very large number of people. So usually in real world also it's usually the case that as you make new friends, maybe like and hang out more with the new friends, then maybe the bonds with the friends which were like of 10 years ago become slightly weaker. Obviously it's not always true, you might choose to stay with different friends also, but every human has different kinds of limits to his or her social circle's size. So Dunbar number is essentially like what's the size of the social circle approximately for an average youth. And usually like studies have found that the average social group size for a person is experimental studies have found that for a human, average social circle size is between 100 and 200. So yeah. So you can like a kind of, so it does not mean like Dunbar number does not associate with like the total number of people which you know. So some people are likely just to be acquaintances, but it just says that the people with whom you can you can be in close contact with, which are like strong ties. So a human on average can have like 100 to 200 strong ties at a time. If you try to make more stronger ties, maybe like there's a cognitive limit to the pain, and you will be breaking off ties with some people of the past, something like that. And this is like again uh, quite a simple thing to see. So like this is again more psychological phenomena rather than a mathematical phenomena. Okay, now let's come to more mathematical terms. Like till now we were just talking about maybe heuristics and like how do those connect to like maybe psychology and something. But now let's come to more mathematical things. So there is this concept of bridges and local bridges in graphs. And so a bridge is a direct tie between nodes that would otherwise be disconnected components of the graph. So what's like intuitively, what is a bridge in a graph? So bridge is an edge, which if you delete, the graph becomes disconnected. So suppose initially the graph was connected, then a bridge in that graph would be an edge on whose deletion the graph will actually become disconnected. As you can see here, like if this edge is present in the graph, then this whole graph is connected. But as soon as you delete this edge, the graph becomes disconnected into two components. And this is why like this edge is a bridge. There are no other bridges in the edge. But note that like this phenomena, bridge, an edge being a bridge, is a global phenomena. Like an edge being a bridge or not is more of a property of the whole graph. So it's a global property because like you will have to, so whenever you want to identify any bridge, whether any edge is a bridge or not, you will have to look at the whole graph at a time and see whether the graph becomes disconnected. So there is this corresponding notion of local bridges also. So suppose we want to like localize this property to some vertex, like how can you say like an edge is a local bridge with respect to some vertex or maybe a vertex pair? So with this, so local bridges are usually defined as maybe, so your local bridges are defined with respect to any pair of vertices. So suppose there is any pair of vertex x and y, then an edge will be a local bridge between those two vertices. If on deleting that edge E, the shortest distance between x and y increases. So local, this is precisely what the statement says, that x and y are ties between two nodes that are shortest route by which information might travel. So essentially on removal of a local bridge, distance between two nodes will be increased to a value strictly more than 2. So essentially what this says is maybe like, so let's just consider maybe these two vertices on the top right, or like on the top left and the top right. So local bridges are kind of local properties where you have to look at only pairs of vertices and not the whole graph. So suppose you are defining some local bridges with respect to these two vertices. Then first you see what's the shortest path between, what's the length of the shortest path between these two vertices. So the shortest path length is 2 because this is like the shortest path in this graph. You need two edges to go from this vertex to this vertex. And now then what will be the local bridges? So suppose you remove any of these edges, like suppose if you remove this edge, then the shortest path distance increases for this graph from like 2 to 3 because now the shortest path will be something like this. Similarly, this edge is also a local bridge because the shortest path then changes to something like this. And any other edge is not a local bridge with respect to these pair of vertices. So with respect to these pair of vertices, these two are the local bridges. These two edges are the local bridges. Similarly, for these two pair of vertices, for this pair of vertices, these two vertices, this edge is a local bridge because right now shortest path distance is 1. But as soon as you delete this edge, the shortest path becomes something like this, this to this to this to this of length 4. So that's why this edge is a local bridge with respect to this pair of vertices. And note that like local bridges and global, the actual bridges are quite different because local bridges deal with like shortest path between pair of vertices, whereas bridges deal with the actual connectivity of the graph. So bridges do not look at shortest paths, whereas local bridges look at shortest paths. Like here in this graph, I don't think there is any bridge present because deleting any single edge still won't cause the graph to become disconnected. But like for every pair of vertices, there are many local bridges present. So I hope it is clear to everyone. Like if there are any doubts at any point of time, feel free to stop me and ask me in chat. So otherwise, maybe we can. Uh, yeah. So then there is this notion of like that there is a metric called edge embeddedness defined for local bridges. So for an edge x comma y, its embeddedness can be defined as number of mutual friends that the endpoints of the edge possess. So like embeddedness for an edge x comma y is nothing but size of the common neighborhood of x and y. And what's a local edge? Local edge is a local bridge is an edge with embeddedness of 0. So maybe this is kind of not relevant. Yeah. Again, a kind of a metric. Okay, and then we can move on to like is page rank. I think we discussed briefly, or maybe we did not discuss, and I left it as for you guys to look at in the lectures only. So yeah, so there were mentions of page rank, I think, in the previous week also, but this time I think page rank was discussed in a bit more detail. So what's essentially page rank on a very high level? Like page rank is uh, like a value assigned to every node of the graph, which assigns some kind of an importance to every node. And then how does page rank capture this importance? So page rank says that a node is more important the more number of in neighbors it has. So more is the number of edges, like more is the number of edges incoming to a node, the more is its importance. And similarly, more the number of outgoing edges of that node, the more is that node importance divided into or like flowed into other nodes. So outgoing edges are known as forward links, incoming edges are known as backward links. So every forward edge establishes like so if there is a like forward node from C to F and C to E, then what this means that suppose C had some importance X, then then the C will divide this importance X evenly between the nodes E and F. So X by 2 importance will be imparted to the node E, and X by 2 importance will be imparted to the node F. And this is like kind of intuition behind page rank. And then maybe these E and Fs are imparted some uh, importance, and then they can forward some of this importance here also. So like suppose E got imparted an importance of X by 2 from here, and suppose Y by 2 from here. So now E has a total importance of X plus Y by 2, and now it has only one outgoing edge. So imparts all of this X plus Y by 2 importance to this web page A. And like similarly, like you can keep doing this process till this process converges to some values. And it was discussed previous week that this will converge to some set of values. And the values to which it will converge are what are called the page ranks. So I hope this is clear to everyone. Then there was then we discussed like the random surfer model for page rank. How can one model page rank as a random surfer model? And uh, what essentially this states is that also like in here like there are some issues discussed related to page rank, like why defining page rank just like this as like a node dividing its importance into its outgoing edges and getting its importance from its incoming neighbors is like kind of a bit flawed, and you need some other modifications which are like maybe adding 1 by n to every node's importance or something. But those were covered in the lectures, and maybe you can see the lecture videos for those things, like what are the issues faced in defining like page rank like this, and how do we resolve them. And then like the resolved model for page rank can be thought of as a random surfer model, which essentially states that, okay, like the values which you obtain here in the page rank, so these values can be obtained in another way, which is like kind of modeling. The same values can be obtained in another way, which is kind of modeling the network as a random surfer model. And what this means is that suppose a random web surfer starts surfing the internet. So like maybe a surfer will start off at a random page P1. So from out of all the available, like let's say n pages, the surfer will choose one page at random with probability 1 by n. And then maybe now the surfer will move to like, now the surfer will start to follow these outgoing links. So, and like choose any outgoing link at random from all the outgoing links present. So for example, suppose the surfer starts here in this node, then there is only one outgoing link from this node. Surfer will surf and go to this node. And now surfer will, again, there is only one outgoing link, so it will go to this node, then this node, and then maybe it can come back to that node. Or like, so surfer can keep surfing like this. But also with, so there's another step, like either surfer can like randomly choose to go to like one of the outgoing nodes, or with some probability like alpha, it can also jump and choose and start to like choose again, like start to randomly surf again. So essentially what is this saying is, so for example, suppose you are surfing the internet, like, then surfing some web pages, and suppose like you have to find out some information about, let's say, some topic. Maybe let's say you want to learn about social network analysis only. So what we'll do is maybe you'll look at a bunch of web pages which are related to social network analysis, open one of the pages at random, and then maybe you'll read up that page and also see if there are some references present in that page, so that you can read some follow-up articles on social network analysis. Then you will again, like, you'll go to one of those pages, one of the pages which the starting page had reference, and you'll start reading that page, and you'll keep following this references procedure till you get, maybe at some point you get bored and you say, okay, maybe I should start all over again, and like, and you again search social network analysis and again choose one of the pages at random and start reading it, and then read it again for some depth, then go to one of the uh, references at random, then read that reference, and then maybe you will get bored again, and then you start this procedure all over. So this is what the random web surfer model captures. So server starts at a random page, and then upon landing at a page pi, server chooses either of the following. So with probability alpha, jump to a random page, and with probability 1 minus alpha, continue its course of following hyperlinks at random. And the more the number of times the surfer visits a node during the above random surfing, the higher is the importance of the node. And like, actually, you can calculate like the probabilities with which the surfer will land at certain page will be exactly equal to the page rank which you obtain using this mathematical procedure. So this random surfer model is mathematically equivalent to the uh, the actual values which we obtain to the page, and this can be proved. So then there is this concept of personalized page rank. So then, like, maybe this personalized page rank concept was introduced because what we can think is, why are we choosing maybe like all of, so one glove fits. So what this page rank policy follows is that one glove fits all, because like what page rank algorithm will do is maybe, okay, maybe just look at the network and find out the probabilities of like hitting all of these web pages at once, and then these probabilities will stay constant, and you'll say that, okay, if there's some web surfer X and some web surfer Y, both will have the same kind of probabilities. But note that like two web surfers might be different people, and so you don't want like so suppose you're doing yeah, what you want is maybe like have some kind of personalizations to the users X and Y. Like maybe X prefers maybe lecture videos more from NPTEL, so you want like a NPTEL social network analysis course to have like more importance, whereas maybe the surfer Y does not like NPTEL and watches from some other source, So you want the surfer Y to show. So you want to show like for surfer Y more importance to the pages which are not related to NPTEL, something like this. So, and how can this be done? So like if you want to do some kind of personalization, maybe this step of like so this graph is fixed. So this web graph is fixed. So you can't really change the out neighbors and in neighbors of a node. But what you can change is this probability, the jumping probability. So right now you're assuming that you jump to a random page PJ and like start the process again. But why do you want to choose one of these pages at random? Like maybe if some person prefers web pages of NPTEL, then those pages can be assigned more probability that after random jump you will land at those pages will have more probability. And with someone who does not like NPTEL, the other pages can have more probability. Something like this. And this is essentially the concept behind PageRank, that the landing page need not be equally likely for all the pages of the graph after the random jump. So surfer may land. So essentially, what personalized page rank entails is surfer may land at a specific page on return. Surfer may land on set of pages. Surfer may land on a list of pages based on his or her search pattern. So then based on a surfer search pattern, you can assign these probabilities of random jumps. And then just the probability will change a bit. Like these mathematical expressions can be kind of seen from the lectures itself. And I don't think this is quite difficult also. So what's the personalized page rank for a node W? It's just maybe, so at any step, either from W, you can do a random jump. So either you will do with probability alpha to some other node, and with probability 1 minus alpha, you will actually be coming to W through some nodes B's. So either you have come to W using this random jump alpha, so this is that part, or either you have come to W using the web surfing, and that is kind of entailed here. So previously this expression was just 1 minus alpha this time plus alpha. Like if you are not talking about personalized page rank and general page rank, but just talking about general page rank. But now this kind of alpha gets replaced by alpha times E of SW, which just entails like with what probability on a random jump will that specific user come land at web page alpha, web page W, something like this. So I hope whatever I'm saying makes sense. If not, like please feel free to ask in chat. Because this concept of PageRank is a bit nuanced, but once you get it, like it's really not that hard. And I think this, what are the advantages of using PageRank? So I think this was just kind of discussed. The mathematics of PageRank was kind of discussed previous week. So if like the PageRank can be computed using a simple uh, system of linear equations, and it is guaranteed to converge to a unique solution using a very beautiful mathematical theorem, which was discussed last week. And yeah, and it is very robust and can be computed quite fast. So yeah, so PageRank has quite a many advantages, but one thing which PageRank lacks is maybe some kind of like diversity. Like it's not necessary that PageRank. So what you usually want is maybe based on your search part. Even if you are going by your search pattern or something, you still need to show some kind of like diverse kinds of results. So you need to assign nodes different importances, but you also want to have these importances as being diverse, that so that sufficiently many large groups are represented adequately. And this is where the concept of div rank came in, which is more like diverse rank. And yeah, so the disadvantage for PageRank was the top rank nodes in PageRank are often not diverse. And what this means is that maybe, so suppose this was the example, this was covered in lectures. So that these three, so higher the size of the blob in the node, the more is important. So if you compute page rank, maybe these three nodes all have equal page ranks, like all have very high page ranks. So these three nodes will have the highest importance in the graph. but maybe it's not a good idea to have all of these nodes as your top three uh, preferences. If one wants to select top three preferences, it's not a good idea to have all these three nodes as top three preferences, because even though all these three have like a high page rank, but these are not diverse. Like these are very near to each other. What you ideally want is you want to represent this side and this side also adequately. That's why maybe it's a good idea to just select maybe one of these. So assign like maybe a high page rank to one of these, and then the other two can be from these kinds of areas. So that in this example, like here you can see that like here also like page ranks are sufficiently nearby different nodes, but now like the selected nodes are diverse. And this is the advantage of DevRank, that you can measure prestige along with diversity also. So these nodes here were also prestige. These nodes are also prestigious in the network because these nodes encapsulate uh, these parts of the network. But these nodes are the most prestigious because they have a large number of nodes nearby. Uh, but you still want like a prestige along with diversity. So maybe just this node was sufficient to capture the prestige for all of this region. And then for this region and this region, you can have some other nodes. So yeah. So this is why this is the use of maybe div rank. For example, if all the top rank places are non-vegetarians and the user is vegetarian, the list is useless. That's why diversity is desirable actually. Okay, I hope it makes sense. Like, why do we need another notion maybe um, from page ranks, which is div rank, and how do you compute? Like, so now we have given an intuitive idea of, so we need something like div rank, but there was a mathematical formulation for page rank also, which was this kind of an equation. And how do you calculate the page rank? So you just solve this system of equations and you will get at the correct page rank. But like, how do you compute div rank? So this is just a heuristic thing we are saying right now, like looking at the figure. But how do you actually capture the notion of div rank? It's through like vertex reinforced random walks. So maybe let's just maybe not get into the mathematics of it. Like you can view watch the mathematics in the lecture videos. But div rank is nothing but vertex reinforced random walks. So we here like what you actually do is just transition probability from one state to the next is just like is also proportional to number of previous visits to the state. So if you are at some vertex x, then the transition probability will also correspond to number of visits which have been done previously till x or something like that. So we are not getting into mathematics of it, but yeah. So and this is how actually you will be able to see that like this works out, and using this one can prove that the ranks generated will be diverse and yet capture all the prestigious things, something like that. Then like after going through stiff rank, then maybe we can then there was this discussion about measuring similarity of objects. So suppose like you have a graph, and like graph can have like nodes, different nodes corresponding to different kinds of entities, completely different kinds of entities even. And then maybe you want like two objects of same type to like you want to find out the some mathematical notion for similarity between the two objects. So one notion is like how can you like identify if two objects are similar? So two objects are similar if they are related to similar objects, and this is like what's done like, and like this is captured mathematically by the notion of simrank. So like, so what simrank does is it assigns every pair of nodes a similarity score. And how do you calculate this simrank? So the formulation for simrank is like quite simple, uh, that for any two nodes a and b, like note that similarity rank between any two nodes always lie between 0 and 1. So similarity between a and b is equal to 1 if a is equal to b, because obviously a and b are similar. And it is 0 if uh, in neighbors of I or in neighbors of B is the set phi. and otherwise it's just equal to like some constant c which we can choose by ourselves. Like it's usually, I think it was discussed in the lectures that this constant c is set to 0.8 or something in real world. Divide by number of in neighbors of a times number of in neighbors of b times like sim rank between all in neighbors of a and b's pairs. Something like this. So note that this quantity will always be less than equal to c, because this s of I, like the similarity, this sim rank between these two in neighbors, I and jth in neighbors of a and b respectively, will be less than equal to 1, because we know that sim rank is always less than equal to 1. And there will be like a number of in neighbors of a times number of in neighbors of b terms here, and all terms are less than equal to 1. So the total so this summation can be at most equal to this denominator. And so like these and these cancel out. So the highest value that sim rank can, this whole term can take is just equal to capital C. And so capital C needs to be less than equal to 1. And it's usually set to something like 0.8 or something. So note that while defining sim rank, first you check whether the two vertices are same. So if the two vertices are the same, then the sim rank is 1. But if one of the vertices has no in degrees, like no in vertices, then like you cannot compute this quantity, right? So you just set its similarity rank to 0. And otherwise you compute it using this formula. So yeah. So similarity between, so this is the basic notion of sim rank. And how do you, maybe I should just leave this upwards like this. This is just what we discussed right now, that if there are two nodes and they are not equal, and either or A or B have no in neighbors, which is the case here, then sim rank of A to A comma B is 0. Like suppose A and B are equal, but they have no in neighbors, then you will say that sim rank is actually 1, because A and B are equal, this criteria is tested first. So even if suppose a node A has no in neighbors, but like similarity of A comma A will always be 1. Like so this criteria, this condition takes priority over this condition. Just note that like this is something which is important and will be useful in one of the problems which we'll be doing later. And like now, how do you compute sim rank? Like as you can guess yourself, maybe we can compute this iteratively, because like sim rank for two vertices depends on sim rank of other vertices. So at some maybe R naught step, just assign some sim ranks to all pairs, and then like at every time step, maybe just keep updating the sim rank values using the formula which we have. And in the limit, like we can say that this kind of algorithm will converge to the actual sim rank values. And then sim rank in heterogeneous bipartite networks is nothing but, so suppose there are users as well as products. Then for users, sim rank can be thought of as like the number of products. Like so sim rank for users will just be equal to like suppose there are two distinct users, u1 and u2, then the sim rank will be just equal to like number of out neighbors of u1 times number of out neighbors of u2, where like out neighbors like so the edges are always between user to a product, because it's a bipartite network. So this is just maybe the number of products associated to u1, number of products associated to u2, and here are like similarity measures between oi of u1 and oj of u2. Like so like this term captures like similarity of objects, because any ith neighbor of u1 and jth neighbor of u2 are products, even though u1 and u2 are users, but these two things are products. So similarity of users is dependent on this similarity of products, and here similarity of products is dependent on similarity of users. So please keep this in mind, like this kind of importance. Like in general in sim rank, you are saying that sim rank between a pair depends on like in neighbors of maybe the pair, or maybe like, so sim rank of a pair of vertices depends on like sim rank of some other pair of vertices. But here, like those pair of vertices have some special structures. The sim rank of a pair of users depends on certain sim ranks of products, and similarly, sim ranks of products depends on sim ranks of users. So yeah, so there's a two-way dependence between users and products here. So to calculate sim ranks in a network, like what can you do is maybe just form all these bunch of linear equations, and then solve these linear equations to find the value of sim rank, something like that. Then there's this notion of heterogeneous networks. So heterogeneous networks is nothing but suppose we have a graph v comma e, and then what are heterogeneous networks on a high level? If you don't want to go into the mathematical definition, heterogeneous network is nothing but suppose like there are different types of nodes. So like this v, the vertices present in v, many vertices have different types. Suppose some vertices correspond to users, some vertices correspond to products, and so on. So this notation like styled A just denotes the set of different types of nodes present. Similarly, styled R is just different types of edges present in the network. So as they can different types of nodes, they can different kinds of edges, and these mapping functions phi and psi map like what node is of which type and what edge is of which type. So yeah. So even though this seems mathematically kind of very notational heavy, but like it's very intuitive. What it's modeling is just a network with different types of edges and different types of vertices. So note that if like this style A is the size of style A is 1 as well as style R is 1, what this means is like uh, there is only one type of, like all the nodes are of the same type. So the style A equal to 1 denotes that all the nodes have the same type, like which is maybe type 1. And similarly, all the edges in R have, all the edges have the same type, which is also maybe let's type 1. So then like if all nodes and all edges have same types, then it's not really a heterogeneous network. But if everything is of the same type, then it's a homogeneous network. And if like these are like, if one of them is at least one of them is greater than 1, then system is heterogeneous because now there are different types of nodes or edges. So, yeah. So I hope this definition is clear. So yeah. Yeah. So for example, like suppose child is, so suppose the number different, the types of vertices is just like 1. So there only vertices are only of one type, but edges are of different types. So yeah, there are more than one types of edges, but only one type of vertices. So for example, like the nodes can, if the vertices represent, let's say, people in a network, then all the people suppose are of the same type, but then the edges between them can be of different types, which can correspond to the relation between the pair of vertices. So these two pairs maybe can be a family type. So they are family, these two people, but these two people are colleagues. So yeah. So basically, we are trying to model different kinds of social networks in terms of these heterogeneous networks or something. Yeah. And then what's a meta path? Okay, maybe yeah, meta path is kind of importance, but okay, maybe like you guys can yeah, maybe we should get to problem solving soon, because like we are already halfway past our session. So like these concepts are also quite simple, like what are meta paths, so you can look at it later in the, like if you have not seen them already in the lecture video. So there are like in heterogeneous networks, how do you define like a similarity between like two nodes or something? So those can be defined using these meta paths. Like how can you say like if all the nodes are different types, so between two nodes which are the same type, like how can you define like what kind of similarity is present? So those kinds of notions of similarity are defined using like these meta paths and like yeah, some random walks on meta paths and so on. But there is another thing which is quite common in these kinds of heterogeneous networks, like, which is important, like, which also has a question based on it on the assignment, is this path sim, which just denotes similarity in terms of peers. So this metric is, I think, like, you can look at these path count and pairwise random walks metrics by yourself later on, but this path sim is something which we will discuss right now. So yeah, so what's the formulation for path sim? So, and between any two objects x and y of the same type, uh, so between any two objects x and y of the same type, the path sim just finds out like the different kinds of paths present from x to y. So 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 similarity between x and y is just equal to 2 times the number of paths from x to y, where x to y is a path of certain type. Like this is where you need, like, yeah. So the type of the path is defined by something like meta path, but maybe we'll get to that later, or you can look at later. But what this means is that, like, suppose like in a network there are some authors as well as papers. Like there are a network is there which has like nodes, as some nodes correspond to authors, some nodes correspond to research papers, and then a path can be like a path can be of the form like author paper author. Like one meta path, a path, one type of path can be like a path of length 3, like maybe length 2, which contains 2 edges, and the path contains, like, the path has like a path of this form that author comes first on the path, then a paper comes, then an author comes. So author paper author, let's say, is a type of the path. So this so then the similarity measure between x and y uh, uh, based on like this type, like this type author paper author will be just twice 2 times the number of paths between x to y which are of type author paper author. So basically this p xy belong to this child p just denotes that the path between x to y is of this form, of this type. So so you'll have to define this type beforehand, like with respect to what type are you talking about this path similarity. But yeah, as soon as you define with respect to what types of path are we saying, then it's just like twice the number of like paths from x to y when x to y's path is of certain type, divided by paths from x to x when x to x is a path of certain type, plus paths from y to y where y to y is of the same type. Yeah. So what this essentially says is that yeah, note that this definition works. So this path sim is more or less defined usually for like undirected networks and not directed networks. And that's why like if you put like number of paths from x to y which are of some type p will be equivalent to like number of paths from y to x, because like usually we assume that the path types are these path types are kind of like uh, reversible, they form a palindrome. Like author paper author is a palindrome because reversing this author paper author type will still result in author paper author, something like that. So yeah, so note that like number of paths from x to x and number of paths from y to y still remains the same even if you swap x and y. Like the y terms come first and x term comes later, and in the numerator, like paths from y to x will be equal to number of paths from x to y because the graph is undirected. And that's why the path sim measure is symmetric. It's also normalized, like you can show this that this quantity will always be less than equal to 1. Like it's not very hard to prove that this quantity like will always be less than equal to 1. And yeah, the idea is maybe because, okay, maybe you can see this yourself. So this thing is always less than equal to 1, and it's maximized when s of x comma x is equal to 1. Like when y and x both are similar, both are equal, then p of x to x, this term will become P of x2x, this term will be P of x2x, this term will be P of x2x. So 2 times P of x2x divided by 2 times P of x2x. So which will become equal to 1. So that's why, yeah, these are like some important properties of path sim metric. Like, this is an important metric for us. Yeah. So what essentially counts is like the number of paths between x and y. So it increases as the number of paths between x and y of certain type increase, and it decreases as like number of paths from x to x or y to y increase. Okay, then. So maybe we can move on to the questions. So more or less, I think the questions won't be too difficult if you have paid attention to like today's summary and also to the lecture videos. So I'll want you guys to participate in this. So I would like if you guys try to answer these questions first. So let's see the first question. So in a network where each edge represents a potential collaboration between two nodes and the goal is to maximize number of such collaborations, which type of network is most suitable? So like, so as I said, like what we have discussed mostly is like, if we are given a network, how do we analyze it? But then another important thing is like to decide like what type of network should we even form for a real world network problem. So the real world problem is kind of like we want to denote an edge to represent a potential collaboration between two nodes, and then like and you want to maximize the number of collaborations. So what kind of network is most suitable? Okay, so as Karpagam has written in chat, so good job Karpagam, that bipartite graph is the most suitable here. So option C. Like, why is bipartite graph very useful here? Because so you always have only a collaboration between two nodes. So what you can do is maybe like have one set of nodes on the left side and one set of nodes on the right side, and then an edge between those two, any of like an edge between left and right side can denote a collaboration. And that's why, like, although obviously like you can model this problem, I think, in trees or as cycles also, but bipartite graph is the most suitable. Like collaborations, like maybe it can be somehow like be written in form of trees or cycles also, but most suitable out of all of these is definitely bipartite. So I hope it makes sense to everyone. If there are any doubts, like please ask in chat. You should see as bipartite network is most suitable to capture the collaboration between pair of nodes. And this kind of thing has also been discussed in lectures. So yeah. Then the second question is in the page rank algorithm, the node with the highest in degree is always the most prestigious. Is this true or is this false? Would anyone like to answer in chat? Like, you don't need to answer it correctly. Like just maybe take a guess also. I'm fine with that. Is it true that the node with the highest in degree will always be the most prestigious node in the page rank? Okay, so Ravi is saying that the answer should be true. Would anyone else also want to answer this? Do you think like it's true or it is false? So actually, Ravi, yeah, on like first look, like it might seem that this argument is correct because this claim is correct because yeah, the more is the in degree, then more prestigious should be that node. But note that this is actually not always the case. Like actually, this statement is false. And why is this? Uh, because in PageRank, like what's done is like so you have some node. So maybe we'll just come to PageRank again. So in PageRank, what you do is you have some node C. So suppose maybe like let's just take some other node which has at least two. Yeah. So suppose web page D has two incoming edges, web page B and web page C. So web page D has two incoming edges. But suppose these web pages B and C themselves are not very relevant. They have very low prestige. So if B and C themselves have very low prestige, then even if they impart some of those prestige to web page D, even still like web page D will not have high prestige. And in the same network, suppose maybe web page E has a lot of prestige. If E has a lot of prestige, then it will impart some of its prestige to maybe web page A. And so, okay, like here maybe these two have equal in degree, but like the high level idea is this only that while calculating page rank, you don't just look at like the in degree, but actually like kind of weighted in degree, or like what I would like to call like the sum of the weights imparted by each of the nodes, incoming nodes. So it's not like a page is not more important if the number of incoming edges are there, if the number of incoming edges are more, but it is more important if the amount of prestige coming through those incoming edges is more. So this B imparts some prestige to web page D, this C imparts some prestige to web page D, but maybe the total is low. So think of this as this thing only. So suppose in a real world network, like in real world, like let's say one person has maybe two referrals from uh, so suppose you are applying for a job, and you have like two referrals from maybe two SD ones, or maybe like two starting level software engineers. You have referrals for some kind of a job, but there's another candidate like who just has one referral, but that referral is more from a like VP or let's say CTO of the company. Then even though candidate one has more referrals in terms of like getting two referrals from like two software engineers, but still like overall the prestige for candidate two will be more preferred because he's getting the referral directly, even though it's just one referral, but he's getting it directly from the CTO. And like referral from CTO holds much more importance than referral of two STs. Just a kind of a heuristic idea. And this is similar here also, uh, like because like here also every page is impart like so every node is imparting like every incoming node is imparting some of its importance to the actual node. Then the more important the incoming nodes, the more is the importance imparted. And so like there can be a node which has just one edge, incoming edge, but the one incoming edge has very high importance, like CT or something. So does this make sense, Ravi Kishore and Karpagam? Like, why should this statement not always be true? Okay, it makes sense. Very good. Nice. Okay, nice. Yeah. As a node can have high in degree, but if the incoming nodes have low page rank, then the total maybe I'll label the node as node X. Then the page rank of X will still be low. So I hope this makes sense, and that's why like this claim is false. Okay. Then for questions 3 to 5, we'll be looking at this figure. So maybe let's just look at question 3 now. So if PEXY represents the probability of formation of an edge between nodes X and Y, then employing the property of triadic closure, what can be hypothesized about the relation P A comma C versus P E F comma D. So what's the probability of a formation of an edge between E and C versus probability of formation of an edge between, okay, no, maybe this is not F and D. I think I meant to write it as E and D. I don't remember. I'll just a second, guys. I think I miswrote this question. I think there's a similar question in your quiz also, so I don't want to like solve actually that question. That's why I have to change it a bit. A to C. It's C to D, so I went C to D. But I'll ask maybe. Yeah. So we can keep it as maybe this. This I think works. Yeah. So so the question is, so we discussed this triadic closure previously, right? So we discussed that try like you can quantify strength of a triadic closure using clustering coefficient, and basically it measures the probability that pair of friends B comma C will also be friends with each other. Like clustering coefficient of A represents whether nodes B and C will be friends of each other, and this is what is asked here. Like assume we are talking about the property of triadic closures. Employing the property of triadic closure, what can be hypothesized about the relation between probability that an edge forms between A and C? So what's the relation between the probability that an edge forms between A and C and the probability that an edge forms between C and B? So what we need to calculate is maybe calculate A and C and the probability of an edge formation between C and B separately, and then answer this question. So would anyone like to attempt this question? Like, although like this question might seem a bit calculated because you need to find maybe clustering coefficients and all, but there is something special about this question, and you can solve it like directly, like even without doing calculations. Would anyone like to point it out in chat? So note that we are talking about triadic closure formations, and yeah, we are looking at the nodes A comma C and the probability of an edge formation between C and B through triadic closure. With the C and B and A and C, like how do you compare the probability? Okay, so Ravi Kishore is saying the answer should be D, that probability between A and C is greater than C and B. And why do you think, Ravi, is this the case? Okay, Venkat is also saying this only. So would Venkat or Ravi, any of you like to explain why is should T be correct? Yeah, actually, like actually your answer is correct, but you also need some reasoning to back it up. So Ravi Kishore is saying that A and C closer than B and C. What do you mean by closure, Ravi? Here, do you mean closer? Like CALOSER, but or yeah. So that's the correct idea, Ravi. So yeah. So good job, good job. So yeah, that's precisely why I was saying this problem can be solved directly. So Ravi saying that A and C, like, so forming for a triadic closure formation, like you need to have the nodes in a triad, right? So for for an edge to form between A and C, this A and C need to be present in some kind of a triad. And the triad is like AEC because these two have common neighbor. A and C have a common neighbor E. So the probability of formation of an edge between A and C can be given by like clustering coefficient of E, right? And clustering coefficient of, okay, but okay, 1 second, guys. I think I have a bit confused myself now. Just let me think about it a little. Yeah. Okay. Yeah, I think clustering coefficient. So essentially, so why am I okay? So why am I getting a bit confused? Maybe I'll just spell it out to you guys. So yeah, like probability of an edge formation between C and B. Let's look at this quantity first. So between C and B, so you need first of all you need a triad for like quantifying the probability of edge formation. But note that between C and B, like C and B can never do not have any common neighbor. Like between C and B, like there is no common neighbor, so you can not form a triad using C and B in this graph. This is precisely what Ravi Kishore is saying. So between C and B, like you cannot you have a probability zero of formation of an edge because of triad closure, because there is no common neighbor of C and B present. So if there is no common neighbor present, then obviously, yeah, you cannot form a triad. So probability of an edge formation between C and B is definitely zero. So this term is zero, and that's why I was saying like it's kind of easy that this term is zero. So and but between A and C here, but if you look at A and C, then they kind of form a triad using this vertex E. So this AEC forms a triad. So now the probability of formation of an edge between A and C is just equal to this thing, the clustering coefficient of E. Right. So clustering coefficient of E is equal to the probability of edge formation between A and C. But why was I getting confused here? Because okay, I think what's the clustering coefficient of E here, guys? Like Ravi, as you said, like their neighbors are same. So probability of formation is equal to clustering coefficient, right? But if I look at clustering coefficient of E here, isn't that also zero? Right. So I also like I was assuming that like this clustering coefficient of E will be non-zero. So like like clustering coefficient of E will also be non-zero. So then non-zero quantity, positive quantity will always be greater than zero. But here, like clustering coefficient of E will just be equal to like number of neighbors, number of edges present between neighbors of E. So neighbors of E are like A and C, but there is no edge present between A and C. So clustering coefficient of E will also be zero, no? Let's just check the definition of clustering coefficient again, but I think like this would be the answer. Yeah. So this numerator term like is kind of zero. Yes, exactly, Karpagam. So clustering coefficient of E is zero because of no edge. Exactly. So yeah, so clustering coefficient of E here, like the how do you find out clustering coefficient for a vertex? You write out its neighbors, so its neighbors are A and C, and you see like how many edges are present between those neighbors. So between A and C, there are no edges present, and you divide it by the total number of possible edges. So there can be one edge present maximum, but zero edges are present right now. So 0 by 1, which is zero, which is what Karpagam has written. Yeah, I think I pointed it out correctly, Sir Karpagam. So actually, I think clustering coefficient for so probability for both of these will be zero then. So then option B and C are correct. Okay, like yeah. So sorry for the initial mistake, guys. I think option B and C are correct. Like option D is not correct. So on the first looks, it might seem that like option D is correct because B and C do not form a closure, but A and C have a like triadic closure. But note that for A and C also, the clustering coefficient is zero. So does this make sense, Ravi and Venkat? Or do you have any comments on this? Like maybe I'll just write down. A zero has vertices C and B do not form, do not have any common neighbor, and hence cannot form a triadic closure. But P of A comma C is equal to clustering coefficient of E, as E is the only common neighbor between A and C. But note that clustering coefficient of E is zero. Hence, P of A comma C is zero. So both of these quantities are zero. Option B and C are correct. Okay. Does this make sense, Ravi and Venkat? I have a bit of doubt, like still, like, but I think this is definitely the correct thing because correct. The string coefficient is zero for this. I'll uh, I'll just like maybe think about it offline also, and if there are any changes to this, I'll update this document. Like, anyways, you have an access to this document, so I'll update this document and write the correct solution if there are any changes to it. But for now, I think options B and C are the correct ones. If there are any changes, like I'll definitely update this. Okay, then it's clear to you guys. So then let's come to the fourth question. So fourth question says that what is the sim rank value between C and B in the network in figure 1? So sim rank value between node C and B. So what's the similarity rank between the nodes C and B in the given network? So yeah. So let's just maybe come look at the definition of sim rank again. So sim rank is, so how do you compute sim rank? So initially, like if A is not equal to B, then sim rank is 0. If A equal to B, then sim rank is 1. And then the formula is updated as following, that Rk plus 1 is C divided by number of in neighbors of A times the number of in neighbors of B. Then Rk of ith in neighbor of A times jth in neighbor of B. So this is the formula for sim rank, right? So let's just keep in mind and maybe get to work. Again, like this problem has a special structure because of which, like this network has special structure because of which, like you don't have to do a lot of calculations. Maybe I'll just copy and paste the network here also. Yeah. So note that initially what we do is initial values we like if we have to do this iteratively, then okay, maybe let's not do this iteratively. Let's just look at the definition of sim rank. So we know that like maybe I just put this as s. So this s is like the sim rank function. So what will the value of sim rank between C and B be? So first you see that these nodes are not equal, right? If they were equal, then sim rank value would already be 1. So uh, the sim rank value will be equal to like the formula which we had, which had some constant C in the numerator. Note that like they do not get confused with this C, which is the node C, and the constant C present in the formula for sim rank. Maybe I'll just write it like this. So C divided by number of in neighbors of node C times number of in neighbors of node B. So the in degree of B is 1, in degree of C is 1. So this will be 1 times 1. And then in the summation, what we have is uh, over all pairs of incoming nodes, their similarity measures. So C's incoming node will be E, and B's incoming node will be A. So then this will be equal to like this times similarity of so C's incoming node was E, so this E comma A. Note that this ordering is important, guys, because like C's incoming node is E and B's incoming node is A. So similarity rank between C comma B is equal to some constant C divided by 1 times S of E comma A. And now what is the similarity of E comma A? You also don't know this constant, but we also don't know what's the similarity value, right? And what's the similarity between E comma A equal to? So note that again you will have to apply the same kind of formula because E and A, these two nodes are yeah. Okay, so Venkat is asking that okay, for the previous question, Venkat is asking chat that a tie is more likely to form between two nodes that share common neighbor. Yeah, I get that idea, Venkat, that a tie is likely to form between two nodes that share a common neighbor. But looking at it quantitatively, like just looking at what was mentioned, that the probability with which the formation is present, like if you want to quantify the probability of formation, then it was discussed that the probability that the nodes are friends of each other is given by precisely this, the value of the clustering coefficient. And clustering coefficient is 0, so that's why I was. But yeah, nevertheless, like I'll definitely take a look at it again, and if there are any changes, I'll update this document. So please, like, keep just check this document. Maybe like I'll check this maybe by end of today night also only. So if there are no changes to this document by end of night, then it is the correct thing in my opinion. What I have done. So maybe like let's just focus on this question for now. So similarity between E and A. So E and A again are uh, different vertices. So E and A are different, but note that uh, now E has in neighbor A, but A has no in neighbor. Like A only has outgoing edges. And we had discussed in sim rank that if I at least one of A or B has no incoming edges, then the similarity score is written as 0. So this is equal to actually 0. This is actually equal to like C divided by 1 times 0. And why is this 0? As A has no in neighbors. And so like this C times 0, so whatever be the value of this constant C, so one might initially think that, okay, we don't know the value of this constant C, how will we calculate the sim? But it just comes out to 0 because like A has no in neighbors. So this is just equal to 0, which is the correct answer. The sim rank between node C and B is nothing but 0. Similarly, okay, so I did this problem now. You guys should try this. What's the sim rank between nodes C and F? So again, you will write it something like this, that similarity between C and F is equal to similarity between A and B times some constant C. Okay, and also like maybe you can assume the constant. I think here you'll need the constant. Assume the constant C equals 1. Like here you will need the value of the constant. I think here you do not need. Maybe I'll just solve this orally since we are short on time, and maybe you can try this out later. So actually, like what will happen is like sim rank of C comma F we have to find out will be just equal to like the constant C times sim rank of E comma B, because like you are here now, and then this is nothing but so E and B both again have this only one in neighbor as A. So this will again be like the constant C times similarity of A comma A. And note that similarity of A comma A is 1 because A is equal to 1. And we have multiplied it by like C twice because like one time when we were writing it as B comma E and one time when we were writing it as F comma C. So answer here will be equal to like C square. So answer that will come out here is like C square. So which is actually equal to 1 here. So the answer will be 1. And maybe you can try this yourself. So I did this orally, but maybe you can try to write this yourself. Try to do this yourself. Right. So I hope you guys get the idea of how did I do this. Like I just took the in neighbors of C and F. E and B were the in neighbors. So similarity between C and F is just some constant C times S of E comma B, which is again some C times S of A comma A. And S of A comma A is 1. So C, then what remains is C times C, which is C square, which is just 1. So I hope this makes sense to everyone. Then maybe we can move on to the 6th question. Okay. Yeah. So this question is related to page rank. Okay, I should page rank. So this was what we had the formula for page rank, like which we already discussed that page rank for a node W is nothing but with 1 minus alpha probability, like you will be imparting the page rank from the incoming nodes, like page rank from the node B, which is divided by the number of nodes, number of outgoing neighbors of B. So RB by NB, and plus like with alpha, so 1 minus with 1 minus alpha factor, like this contribution will be there in page rank of W, and with alpha factor, the contribution will be through the random jump, which will just alpha times E of SW, like with how much, like alpha times the probability with which you will land at SW. And this is the problem, and this is what is given to us in this problem. So we are given this, so we have to find out the personalized page ranks when we have this E as 1 by 5, 1. So right now we have these E's as 1 by 5, 1 by 5, 1 by 5s and everything. So like all of these are, so we have like a initial iteration, the R0 is the initial iteration of the page rank. So we have the initial iteration values of page rank as 1 by 5, 1 by 5, 1 by 5. And we also have that the distribution, like the probabilities of random jumps in this personalized page rank is like uniform. With 1 by 5 probability only, it will jump to all of these nodes. And now what we have to find out the page ranks for all the nodes. And note that these R naughts and R, all these are, let's suppose, in order of A, B, C, D, E. So like this is like the initial page rank of A, initial page rank of B, initial page rank of C, D, and E. So let's just find out maybe page rank. So, let's just find out R1 of A maybe. So what will be the value of R1 of A? So it will be first with 1 minus alpha probability. So with 1 minus alpha, where alpha is 0.7. So it will be 1 minus 0.7. With this, you will be imparting the page ranks received from all of the in neighbors. So, so what you want to do is like, so this A gets page the page rank from all of its in neighbors. So note that the in neighbors for A are only like, so this is outgoing, this is outgoing, this is outgoing. There's only one in neighbor, which is C. And C had a page rank of 1 by 5, but how much can it contribute to? Maybe I just put this like this. So this, maybe I should write a formula here. It will be easier for me. Third question. Yeah. So it will be like 1 minus 0.7. This. So it will be 1 minus 0.7 times the total page rank received by the node A. And how much can it receive? So it can receive just from C. And how much will it receive from C? I'll just do this. So it receives like 1 by 5 divided by, so C's whole page rank is 1 by 5, and it gets divided into like all of its out neighbors evenly. So how many out neighbors of C are there? So there is one out neighbor B and another out neighbor A. So 1 by 5 divided by 2. So this is the page rank of A from this incoming nodes. And then with probability alpha, you will be doing a random jump. So alpha is 0.7. So this will be 0.7 times the factor E. And E is just 1 by 5. So this will be just 1 by 5. So it will be something like this. And so this whole expression is like the page rank for A. This will come out to be, I think, 1 minus 0.7 will be okay. Okay, I hope this question is not already present in your. I'll just check if this question is present in your quiz or not. If it is present, maybe I'll just change this question a little. I think a similar question is there, but I thought I changed the values of it. Yeah. So here, like we have assumed alpha is 0.7. I think in the problem for you guys, its alpha is 0.8. So yeah, so we're pretty much safe. So maybe we can get to it. Just a second, guys. Yeah. So what will this value be? So this will be like 0.3 times 1 by 10. So it will be 0.03 plus 0.7 divided by 5, which will be something like, I think, 0. This will be 0.14 plus, so this thing will be 0.14 plus 0.3 times this, so 0.03. So it will be something like this, which will be 0.17. Yeah. So this will be 0.17. And then maybe we can try to calculate similar things for R1 of B. So R1 of B is nothing but 1 minus 0.7 times. So now we'll have to look at B's in neighbors. So I hope this calculation makes sense for everyone. Now we'll do it for B. So for B, B's in neighbors are A and C. So note that you have to take the R0 values, because now in R1, while calculating for R1, like you won't take like the page rank for A, what you will assume here, the contribution from A, you won't assume it to be 0.17, you will assume it to be 1 by 5. Because while making the R1 iteration, you have to take values from previous iteration. So for B, what we have is page rank is imparted from A, and what's A's page rank? It's 1 by 5 divided by out neighbors of A. And what are the out neighbors of A? Number of out neighbors is 3. So A has 3 out neighbors. So it's 1 by 5 divided by 3 plus what's another in neighbor for B? So another in neighbor for B is the C. So C is, and C will impart, like C had 2 out neighbors which we had previously. So these are the 2 out neighbors. So C will impart a factor of 2. And there is another, is there any other in neighbor for B? No, like there are 2 in neighbor and there are 2 out neighbors. Okay, so this is the only thing. And then with probability 0 and with factor like 0.7, it will just be like stay at this place, and this, like maybe you can like solve these expressions by yourself. This will be the expression, but you can solve like what value it comes to. And then similarly, if you do it for R1 of C, okay, maybe I think since we are getting out, since it's getting out time, maybe like you can calculate. So I think you guys now have the idea, like if you have calculated for A and B, how to calculate for C, D, and E. So maybe this is just a try it yourself exercise. That find the first iteration page ranks for C, D, E. Yeah, maybe. So we'll, yeah, Karpagam, here the value of E is 1 by n, like it's given to us already. Like it's given here 1 by n, but it can be different also. Like whatever would have been the value of E, you would have specifically put in those values in the second factor. Yeah, good job spotting it up. I think we need to move a bit faster. So I think today's session is getting delayed. Okay. Yeah. So in the above example, so in this problem, the problem 6, like if we modify the E vector from a uniform distribution. So right now E vector is a uniform distribution, right? The E vector is just 1 by 5, 1 by 5, 1 by 5, 1 by 5. Like, yeah. So E vector is right now 1 by 5, 1 by 5, 1 by 5. And then if we change it from a uniform distribution to focus on 1 or more relevant pages, the resultant page ranks can be termed as, so if it's not uniform, then E is like some other distribution, then we already discussed that it is called personalized page rank. So option C, as discussed in the lectures. So sense. Then the eighth question is, which of the following are properties of path sim? So path similarity measure, I think we already discussed that it is symmetric, as well as normalized, as well as self-maximized. Like, I think we already discussed this, that all of these three are properties of path sim. So yeah. So these are just questions from directly from the lecture. So I won't be discussing these right now. A, B, C, correct. As discussed in the lectures. Okay, so I think this was also discussed in the lectures, like what are time heterogeneous and random walks. So, uh, so like the vertex. So when we discuss that vertex weighted random walks, which uh, yeah, this vertex reinforced random walks, these are called like, these are also called like time heterogeneous random walks. And why is this? Because the transition probabilities at any stage are not fixed, they are reinforced by number of previous visits to the state, so this changes over time. So if the transition probabilities in a random walk change over time, then those are called time heterogeneous random walks. Like what are time homogeneous random walks? The random walks where transition probabilities do not change over time, but if they change over time, then they are called time heterogeneous random walks. So the change can either be increase or decrease. It's like not monotonous. It can either increase or decrease. So it's just like which can change over time. So this also has been discussed in the lectures. As discussed in the lectures. Okay. So these are questions 10 and 11, not 9 and 10. Maybe we can use the questions to the next page. So what we have here is a restaurant user review network. So here you have like restaurants on this column. You have restaurants which are main pavilion, symposium, skyroot, and there are some users who have reviewed these restaurants. So Michelle, Alice, Bob, and Eve are users. So there are objects of two types in the network, restaurant and user. So there exists a review relationship between U and R. So what this means is like uh, between a restaurant and a user, there is a review relationship, which is given by this number. And this number shows the number of reviews given by a user to a restaurant. So Michelle gives a review 4 to Pavilion. And similarly, Alice gives like 4 reviews to Symposium, and so on. And now what we want to find out is the value of path sim between Mint and Symposium. So now note that the type of path which we are talking about is these types of paths. The restaurant review restaurant kind of path. So like so now we want to find out the paths in between Mint and Symposium. So we already discussed what's the formula for path sim. It's just like maybe I'll just write it down. So paths in between Mint comma Symposium is nothing but a so twice the number of paths from X to Y. Here X is Mint, Y is Symposium. So twice the number of paths from Mint to Symposium. And what are number of paths from Mint to Symposium? So either the path can go from Mint to Michel via these two edges, and then Michel to Symposium via these two edges. So Mint to Michel has like, so if suppose between Mint and Symposium, Michel is the common path. If the Michel is the common user, like the paths are of the type restaurant user restaurant. So if Michel is the common user, then it's something like there are two ways to go from Mint to Michel, and there are two ways to go from Michel to Symposium. So it's like 2 times 2. Okay, so maybe like twice of the, we are doing twice the number of paths, and the first term will be through Michel, which will be like twice 2 times 2. And then we have, if the user is Alice, uh, then what we have is Mint to Alice is 4, and Alice to Symposium also there are uh, 4 ways. So this is also 4 times 4, because you can go from Mint to Alice in 4 ways, and then Alice to Symposium in 4 ways. But suppose the common user is Bob, then Mint to Bob has 0 ways. So then there is no way, like even if there are some ways from Bob to Symposium, they are also 0, but you'll have this as 0 times 0. And then the fourth term will be, if the common user is Eve, then Mint to Eve is 0, and Eve to Symposium, okay, again is 0. This is 0 times 0 plus 0 times 0. And this is divided by the total number of paths from x to x plus y to y. So total number of paths from Mint to Mint. So what are the paths from Mint to Mint here? Number of paths from Mint to Mint will be, if the common user is Michel, then there are 2 ways to go from Mint to Michel, and then 2 ways back. So it will be like 2 square, like maybe 2 times 2, plus Mint to Alice, Alice to Mint will be 4 times 4, and then Mint to Bob and Bob to Mint will be 0 times 0, and Mint to Eve and Eve to Mint will be 0 times 0. And yeah, similarly, we need to add the paths from Symposium to Symposium. So this will be like Symposium to Michel, Michel to Symposium will be 2 times 2. Maybe I should write it as, yeah, this is fine. Then Symposium to Alice and Alice to Symposium is 4 times 4. Then it's Symposium to Bob is 0 times 0. And then it's again 0 times 0. So this is the value of path sim. And what does it come out to? It's like 2 times 2, 4 plus 16. So this is 20. So this is 20 times 2, which is 40. So this is 40 divided by 20 plus 20, which is 40. So this is actually equal to 1. And you can see, like, why is it the case? Like Mint and Symposium have almost have the same, are identical in terms of user reviews. Like Michelle Alice 2400 2400, and that's why it comes out to 1 anyway. So this is the correct answer. So paths in between Mint and Symposium is just 1. Karpagav, do you have any doubts? Like, what do you mean by white wise? Oh, you mean this? Like, why are we multiplying it by 2 in here? Like, it's in the formula for path sim that you do twice the number of paths from x to y. Like, it's in the formula itself. Like, this 2 factor is in the formula itself. Like, I'm not doing it. I'm just doing it by the formula. So formula is twice times, and then I wrote down the paths expression. Okay. And now we want to find out the peer restaurant for Sky Route. So what's the meaning of peer restaurant? So this was discussed, I think. You see, so peer restaurant is just the restaurant which has like the highest path similarity with respect to peer restaurant is the, so a peer in a network is just like this was defined here also, like, so yeah. So favor peers, so objects with similar visibility and strong connectivity. So like uh, the node which has the highest path similarity with respect to a node is called its peer. So peer restaurant for Skyroot will be the restaurant which has highest path sim with Skyroot, like apart from Skyroot itself, obviously. Like, so which of these main pavilion or symposium is closer to Skyroot will denote the peer. It's the restaurant which has highest path sim with Skyroot apart from Skyroot itself, because obviously like path similarity between Skyroot and Skyroot itself will be equal to 1. So we need to find out one out of min pavilion or symposium which has the highest path sim. So I'm not doing this. I think you guys can do this also yourself. Because like what you guys just have to do is just like we found out paths in between mint and symposium, just find out paths in between Skyroot and mint, Skyroot pavilion, Skyroot symposium, and then take the, and whatever value is the maximum, then that restaurant will be the peer restaurant for Skyroot. I hope this makes sense. Okay then. So I guess this was it, what I had for the day for questions. So yeah, today I think you guys have a lot of things which you can try yourself. So this 11 question, I think, like, although we have discussed the high level approaches, but there are still things to fill in, which you guys can fill yourself. Here you can find out the first iteration page rank yourself. Similarly, this also we discussed, but I just thought like you can complete it yourself. You can write the arguments down yourself. And this is like something which I will just check and get back to you guys. Like, I'll update this document if there are any changes by tonight. Okay, then. So overall, I think like we spent more than half the session, I think, discussing about the summaries of the lectures, and then in the remaining time, we solve these problems. Okay, guys. So I guess this was it from my side. Since we are already out of time, maybe we can take down for a couple of minutes if there are any. If there are no doubts, then I think we can close the session. So, are there any doubts, anyone? Okay, so Karpagam is typing. Okay, so there are no doubts. Okay, okay, Venkat. Thank you, Venkat, for joining. Okay, guys. So then, since there are no doubts, I guess we can close the session. So once again, thanks a lot for joining today's session, guys. Hopefully, I'll see you guys next week also, same time, 6 to 8 p.m. Monday. So till then, goodbye, guys. I'll be stopping the recording and you can leave the session. Bye bye.